we are rounding off our list of standard integrals. Okay. Now you will recall these results, even if in class you haven't derived them yet and why they are. You have seen them, okay, and they are there on your sheet. You'll remember as well why there isn't a corresponding one for cos inverse on the standard integral sheet. Why is that? Because it's hidden in here, isn't it? It's just the negative of this, right? So you can integrate this and just as easily get to negative cos inverse. You'll just have a different constant, won't you? Okay. All right, that's all fine. Now today we're going to address the two last of the standard integrals that are on there. Unfortunately, there's not any real nice, elegant, simple way that I can, like I did with the inverse trig derivatives, derive them for you. I'm just going to do the tried and true method of, if I could differentiate something and get this result, right? Generalizing from what I'm doing here, I can make an integral statement of this. I can say the integral of f dash with respect to x should take me back to my original offset by a constant, okay? Provided, of course, you can work out what this original function is and then choose to differentiate it, then you can make this statement, okay? So, we'll do this in a couple of steps and then we'll fill out this so it's all nice and neat, okay? So, that's why I've got this off on another side. Let's consider. Okay, now here's the function I'm looking at. Let's have a look at this guy. Yeah. Is it plus? Yeah, it's plus. Good. Okay, now this is really simple. You don't need to be extension 2 students to know this. Okay, I should prop some brackets there. It doesn't look like it's going to become anything special, does it? But let's just walk through it anyway. One piece at a time. What do we start with? 1. Good. Okay. Now hopefully you can see enough here that I don't have to rewrite in index 4. What's the derivative of this guy going to be? It's chain rule, isn't it? What should we start with? Inside or outside? Go get inside.
Outside.
I heard inside first. Okay. So the inside, of course, is 2x. Excellent. Okay. Now what you've got on the outside is some function to the power of a half. Okay. So I'm going to multiply by the power, and I'm going to reduce the power by 1. Yes? Now, being that this is a half, when I reduce it by 1, I get negative a half, right? Which means it's still a square root, but it's on the denominator. Okay, so I'm getting this. Okay, so far so good? Yeah? Okay. So I've got 1 plus, that just becomes x, doesn't it? Bless you. Now, again, doesn't look like there's anything particularly unusual about this. I'm just going to put this all in a common denominator though, because then you'll be able to see something interesting, okay? Because that's just 1, right? It'll be the square root of x squared plus a squared on the square root of x squared plus a squared, right? So I'm just going to get this business. X squared plus a squared plus x. Now the reason why this is interesting is because it is so similar to the function I started with, right? This, the numerator here, is exactly the same as this, right? Okay. So therefore, I'm going to take advantage of this. We'll keep going over here. And I want to consider what happens when I take the log of this function and differentiate that. Okay? So I differentiate log of all of that stuff. Okay? Okay. Now, it's chain rule, but we've already worked out f dash, haven't we? It's going to be f dash on f. F dash on f. What's going to happen? What's going to happen? Because this numerator here exactly matches, the numerator of f dash exactly matches f, it's just going to cancel out completely. In case it's the afternoon, so you know your brain's a bit fuzzy, let me write it out for you. Here's f dash. All over this. There you go, there's f dash. And I'll write it in the correct order just to make the cancelling a little more obvious. There's f. Is that okay? So you get some grand cancelling happening, and all you're left with is this. Okay? So, now I'm going to come over here. This is my 3a result. I'm getting to my standard integral now, okay? The derivative of this log function awkward as it seems, okay, ends up being something quite nice and simple. And it is very suspiciously close to our inverse sine and inverse tan functions. If you're like me, when I got to this point, I actually got quite confused because they look so close to each other. This result, and this result, they can be quite easily mixed up. So be careful. Okay, that's the derivative statement. So of course the converse integral statement just takes this guy, slaps him on the left-hand side with respect to x, and that's going to be my log function, offset by a constant. Okay. Now, I mixed something up here. Sorry. Not that it matters, but it's easier to see the next result if I put that in the right order. I want you to have a look through where I started from here all the way down through to here. Okay? Now, tell me, what significance does this a squared have? The a squared, right? What significance or what change does it make to the derivative that I end up getting? Did I ever have to take into account the value of a squared? I didn't really, did I? Right? Every stage when I did like the inside derivative and so on, I more or less ignored it. Right? It never became a coefficient of anything really. So therefore, this a squared, I can actually sub it out for anything I like. That's a bit weird, isn't it? The reason why they put it like this is because it draws the parallel between all of these. Okay. So therefore, this is the last of the standard integrals. Hardly worth being a different integral really, but I can take this, and if I make an x squared minus a squared, right, so it is still another constant of some kind, which again is not going to factor in if I did the whole process again with a minus sign. It's going to be log of, and it'll be the same, except with a minus sign. X plus